Hi, I'm Dan Crane. I'm a professor in the biology department here at Wright State University in Dayton, Ohio. And this video is going to be my chance to talk with you a little bit about some artifacts and noise issues that come into play when we're interpreting forensic DNA profiles. In short, things that can make DNA profile interpretation just a little more complicated than I think any of us would like. Like all of the videos in this series, the PowerPoint slides that I'll be using, as well as much additional information, will be available at www.bioforensics.com. Check it out. I think you'll enjoy the things that you find there. But with that out of the way, let's just get straight to the task at hand, and that is talking about some of the issues that can arise in terms of artifacts and noise when we're looking at DNA profile results. This particular slide is essentially an outline of what it is that we'll be talking about during the course of this video, and pretty much in the order in which I'll be going through these things. Let's start by talking about technical artifacts, essentially things that happen during the course of testing that can't really be reproduced and really aren't reflective of the DNA that's associated with a sample, but nonetheless are things that we recognize and see happening quite frequently when we're looking at DNA test results. And then after that, we'll get to talking about looking at distinguishing between signal and background noise that might be associated with some electropherograms. But again, the first thing here is let's talk about a very commonly observed technical artifact known as stutter. All right? Again, this is an artifact, and here's a picture of an electropherogram. I would hope that you're familiar with these from having looked at some of the other videos in this series. We're seeing here some information from a single locus. The locus itself doesn't matter, but there's a 15 allele and a 19 allele, right? And we know that they're there. They're tall, strong peaks. They've been labeled by some computer software that's told us that those rise above the criteria that we tend to look for to designate something as a peak. And yet, if you look carefully at this particular electropherogram, you'll notice that preceding both the 15 and the 19 peak are other peaks, small peaks, but nonetheless fairly obviously present. Right? So we'll have some arrows that show you exactly which peaks I'm talking about here. And you could probably also figure out, without my telling you, that those two small peaks correspond to where it is that either a 14 or an 18 allele would appear on this same electropherogram. Those are stutter peaks. Right? We appreciate that during the course of PCR amplification that goes on to generate these DNA profiles, that the DNA polymerase that's doing the job of PCR amplification sometimes has a little bit of a hiccup. It slips a little bit forward, sometimes it slips a little bit backward as it's making copies of the regions that are being looked at for these DNA profiling tests. And when it does that, it makes a product, a PCR product, an amplified bit of DNA that is often a little bit shorter, 1 4-nucleotide repeat unit, if you want to be technical, shorter than the true fragment that was being amplified. And those smaller fragments give rise to peaks that are just before the peak that corresponds to the DNA that really was present in the sample. Those smaller peaks, those little bit of additional PCR product, those are what we call stutter peaks. They're fairly easy to recognize because stutter peaks tend to be found in the position immediately before the peak that gave rise to them, and they tend to be much smaller in height or area if you prefer to look at your peaks in that perspective. So these two peaks, the 14 and the 18, are fairly easily identified as stutter peaks. In other words, they're identified as artifacts, and we're usually not that concerned about the possibility that they might correspond to DNA from some actual contributors to the sample. We recognize them by their position, we recognize them by their height, and if you're curious as to why it is the computer software did not label the 14 and the 18 peaks, it's because the software that was used to attach the label to the 15 and the 19 peak also is invoking something that's known as a stutter filter. Any peak that's in the position immediately before a peak that is less than some cutoff, typically 12%, sometimes 8%, sometimes 15%, but in that range, if the peak that precedes a peak is less than that amount of the height of that following peak, it's simply not labeled, and it's written off as an artifact known as stutter. So there's our first technical artifact, stutter. Right? Very commonly encountered. In fact, it's unusual to find a peak on an electropharogram that doesn't have a stutter peak associated with it. Right. Let's move on. Talk about another technical artifact. Let's talk now about spikes and blobs. Right? I'm sure everybody's heard of the attack of the blob. Well, blobs manifest themselves on DNA profiles as well. They're relatively uncommon, but nonetheless something that DNA analysts recognize readily. Here's what's going on with a spike and a blob. Very simply, a spike is a peak that you see in an electropharogram that is simply too tall and skinny relative to what we would expect for a typical peak. Typical peaks have a sort of expected range of height to area or height to width ratios. If a peak is very narrow and tall, that is an indication that it's a spike. If a peak, in contrast, is short and squat, that is an indication that we're talking about a blob. What gives rise to these artifacts of spikes and blobs? Well, again, they're artifacts. They're not inspired, they're not rooted in any DNA that's associated with the sample. Instead, it's an artifact of the testing process. The particulars as to what gives rise to spikes or blobs is probably not that important. Many have said that there are voltage spikes that are running through the genetic analyzers that can give rise to these phenomenon. Sometimes we're talking about particles that are passing through the capillaries or pieces of dust moving in front of the CCD cameras. The particulars as to what gives rise to spikes and blobs, frankly, aren't that important. What's important is that a DNA analyst can recognize them and say, hey, this is not something that's rooted in the DNA associated with the sample. It's an artifact. It's not necessarily something that's reproducible. Because it's an artifact, we can disregard it. All right? And how are those spikes and blobs recognized? Well, this particular slide is showing you a study that has been performed that shows that you can get an expected range of height to area ratios for peaks that we know are good peaks. These are peaks that came from reference samples, from positive controls. We knew that those peaks were really there and real peaks. A normal peak has a certain range of the ratio of its height to its area. Spikes, in contrast, which we knew were not part of these reference or positive control samples, fall outside of that range on this side of the graph. And while for this particular study we didn't observe blobs, they would be up on this part of the graph. So again, bottom line, spikes and blobs are artifacts. The reality is they happen. They can be recognized and they can be discounted during the course of the interpretation of a DNA profile electropharogram. Let's move on to talk about a third artifact. We're cruising here, aren't we? Because here's a third one, this idea of peak height imbalance. Let me tell you what I mean by peak height balance before we start talking about peak height imbalance. I think it'll go a little bit more easily that way. This particular slide is showing you, once again, a fairly standard, kind of normal looking electropharogram. You know, I could quiz you here and I could say, well, what can you tell me about this electropharogram? One of the things that jumps out to me is that there's never a locus where I see more than 2 alleles. There's information for quite a few loci, and yet every locus has at most 2 alleles. There's 2 here, there's 1 there, 2 there, and so forth. So this looks like a single source sample, and that's good because I can tell you it comes from a reference sample. So it comes from a reference sample, but let's talk about the balance of the heights of these peaks. Let's look at this one in particular, at the D3 locus. Bear in mind what it is that's taking place during the course of this analysis, right? We can see that some computer software says that there's a 16 allele and a 17 allele present. If you're starting to get familiar with looking at these electropharograms, you'll also recognize that the number underneath the name of the allele is the height of the peak as it shows up on the electropherogram. So this 16 is 1,463 relative fluorescent units tall, or RFUs, and the 17 is 1,490 tall. Right? So that's what we're seeing when we look at this particular locus, and that's probably what we would expect to see if we were talking about a reference sample. And again, that is what we're talking about for this particular electropherogram. I say it's what we would expect to see because if you think back to what was happening during the course of the generation of this DNA profile, is that a PCR step took place that was amplifying up the DNA that was present at the D3 locus. And in this individual's DNA, for every time there was a copy of the 16 allele, a chromosome that had the 16 at the D3 locus, there was also a chromosome that had a copy of the 17 allele at the D3 locus. And so at the start, there were equivalent amounts of 16 and 17 in whatever material was collected from the individual who gave rise to this reference sample. Right? They started out with equal amounts. And after one round of amplification, the amount of the 16 should have doubled. And after one round of PCR amplification, the amount of the 17 should have doubled. They should have doubled about the same because they started out the same. After a second round of PCR amplification, there would have been another round of doubling, fourfold increase in the starting amounts. And I think you can see how this plays out over the course of 28 rounds of PCR amplification, 28 rounds of doubling. The heights of these peaks are proportional to the amount of material that was present before the PCR amplification began. And sure enough, we see that these peaks have very similar heights. A moment ago, I said that I wanted to start talking about peak height imbalance by drawing your attention to peak height balance. These peaks are pretty well balanced. How well balanced? Well, we can put a number on it. The number for their peak height ratio is pretty easy to obtain. All that we're doing here is taking the height of the smaller peak, here, the one that's 1,463 tall, and dividing it by the height of the taller of the two peaks, here 1,490 RFUs tall. That'll give us a fractional value, here 98%. The peak height ratio of the 16 to the 17 is 98%. Those are well-balanced peaks, much as you would expect for a single source sample where equal amounts of the 16 and 17 were being contributed. And that's not the only locus where we're seeing peak height balance. We can look to another locus here, this one step further down where we see a 16 and a 17. In this other electropherogram here, the heights of these two peaks are very similar, 633 relative to 661, 96% for their peak height ratios. Right? So here we're seeing what we find when peaks are in balance, when the peak height ratios are looking good. But now let's take a look at some peak heights where there may be some imbalance. So I'd like to draw your attention over to this locus at the D16 part of the electropherogram. Here you see there's a 12 with a height of 372, a 14 with a height of 165. 165 divided by 372 is 44%. Right? Those peaks aren't looking like they're the same height. There's an imbalance there. What could that mean? It could mean a couple of things. It could mean that we're actually here not looking at a single source sample, but rather DNA that's come from two people. One person perhaps contributing a 12 and a 12, and another person contributing a 14 and a 14. Maybe they didn't start out with the same contributions. Maybe the guy who gave the 12 contributed more to the mixture than the person who gave the 14. That is a viable explanation for this imbalance in the height of these two peaks. There are alternatives. Maybe we're looking here at a mixture of a 12-14 individual with a 12-12 individual. That would also explain what we're seeing with this peak height imbalance. Both of those explanations, though, are mixtures. And remember, when we first looked at this electropherogram, our thinking was that, gee, there's never more than 2 peaks at a locus. That's the sort of thing we expect to find for a single source sample. Maybe we need to revise that thinking and start entertaining the idea that this might be a mixture. And if you've watched some of the other videos in this series, you'll know that we treat mixtures different statistically than we do single source samples. So maybe this is a mixture. Maybe what we're seeing here is simply some sort of artifact associated with the reality that these peaks aren't very tall to begin with. There's this phenomenon known as a stochastic effect, just a sampling error problem that starts to rear its head, cause problems for DNA analyses when we're talking about small amounts of starting material. Maybe the reason the 12 is taller than the 14 in this particular instance is because the 12 just got lucky in the early phases of the PCR amplification and managed to attract the attention of a DNA polymerase better than the 14 did, and that carried throughout the rest of the process and causes us to see a 12 that's higher than a 14. So maybe what we're looking at here is a mixture. Maybe what we're looking at here is an artifact that's associated with a small amount of starting material that gave rise to these 2 peaks. Maybe the 14 allele has some sort of mutation associated with it, such that it just doesn't get amplified as well as the 12 does. The technical term for such a mutation, the most common form of such a mutation would be a primer binding site mutation. So there's a lot of things that start to raise red flags. We have questions when we see peaks out of balance. This is a pair of peaks that are out of balance. And the threshold where we start to get concerned about peaks being in balance as opposed to being out of balance is actually something that every testing laboratory is expected to determine using their own protocols independent of each other when they first open up the labs and then when they first start using the testing kits that they'll be employing. While they're supposed to be independent, most testing laboratories have gravitated to pretty much the same threshold or thresholds. Many laboratories use a cutoff of 70% peak height balance. Others use a threshold of 60% peak height imbalance, and there are just a few rare instances of cutoffs that are other than those two. What those thresholds mean is this, is the testing laboratory is essentially saying, if we find a pair of peaks that are above that threshold, where the height of the smaller peak divided by the height of the taller peak is above that peak height balance or peak height ratio threshold, we'll say that those peaks are in balance. They appear, they're acting as they would as if they had come from a single source sample and there had been no other problems with the amplification. However, if the peaks fall beneath that threshold, the labs are essentially saying that there's a potential issue here. Maybe what we're looking at is a mixed sample. That's an indication that we may have a mixture. They're also saying maybe it's an indication we're dealing with small amounts of material. Maybe we're talking about an instance here, one of these rarer instances of primer binding site mutations. Those are considerations that will begin to complicate the interpretation of these test results. All right? But for peaks that are in balance, those aren't concerns, and we can simply move on. For those that are out of balance, we have to start wondering if maybe we're getting something more to the story than this just being a straightforward single-sourced sample where we've gotten a complete set of information from everything that has generated a testing result. All right, so there's a little bit about peak height imbalance. Let me move along now to talk about the fourth of these 4 technical artifacts that I'd like to explain to you during the course of this video, and that is what's going on with this phenomenon of degradation or inhibition. Well, this next slide simply defines for you what it is that's in play here for degradation and inhibition. And the two of them get married together quite simply because it's very difficult to tease apart when we're seeing degradation as opposed to inhibition and vice versa. So very often analysts will sort of merge them together and say that a sample is either degraded and or inhibited. Okay? The degradation part is pretty straightforward. Bear in mind, DNA is a chemical. And like any other chemical, it can interact with other chemicals. And sometimes when DNA interacts with other chemicals, it comes out a little bit the worse for wear. It gets broken, very simply. It gets degraded, right? In some sense, we're starting to talk about the digestion or the deterioration of a DNA molecule. When that happens, when DNA molecules get damaged, they can't be amplified through that PCR amplification process, and they can't contribute to the electropherograms, or at least not as much as they could have before that damage or deterioration had occurred. Right? So degradation gives rise to peak heights on electropherograms that are smaller than they would have been if the material had not been degraded. And now I think it's pretty easy to explain what's going on for inhibition, because sometimes it's not that the DNA itself is damaged. Sometimes moving along with the DNA is some chemical or something that's causing it to be hard to get the DNA polymerases to do their job during PCR amplification. Bottom line, DNA doesn't get amplified as much as it would have in the absence of those chemicals, those inhibitors. And since they don't get amplified as much, we see smaller peaks. Funny thing, the bigger a fragment of DNA is, the better a target it is for degradation, and the more likely it is to be affected by inhibitors during the amplification process. Let's consider those separately for just a moment. It's simply a matter of target size. When you're talking about a large DNA molecule, a big target is more likely to get a hit from a random bullet, in this case a random passing chemical, than a smaller target. A big fragment of DNA, an allele that corresponds to a big chunk of DNA, is more likely to suffer from degradation than a smaller one in the same mix. A big piece of DNA takes more time, is harder to get amplified during the PCR amplification process than a small one. If we've got something in the mix that's making it hard for the DNA polymerases to amplify the DNA during PCR amplification, that effect is going to be observed more for the biggest pieces of DNA than for the smallest pieces of DNA. And so how does this manifest itself on an electropherogram? That's the big question, and that's what I hope that you're eager to see. This particular slide is showing you a sample that has very little in the way of degradation or inhibition. In fact, there's no really obvious signs of degradation or inhibition, and the reason I say there's no obvious signs is that from left to right across the electropherograms, the peaks all have pretty much the same height. At a locus where the individual is homozygous, the peaks are pretty tall for all the other homozygous loci. At a locus where the peaks are for a heterozygote, where we see two peaks, the peaks within the locus are about the same height, and the peaks are similar to the other heterozygous peaks that you see in that same electropherogram. And so we could just draw a line, straight line, a parallel line to the baseline here that pretty well characterizes the heights of these peaks. And the key here again is from left to right, that line is flat. Those peaks have about the same size. But remember, when we're looking at electropherograms like this, the smaller pieces of DNA are the first ones that come off the capillary during that capillary electrophoresis, the size fractionation that takes place in a genetic analyzer. Those are the ones that come off first, the small ones. They race through the capillary. It's the bigger pieces of DNA that take a long time to work their way through. They show up as peaks on electropherograms at the right-hand side of the electropherogram. All right? And so here again, the key is we're seeing peaks on the left that are pretty much the same height as peaks on the right. This is not a degraded or an inhibited sample. But let's change gears a little bit and talk about what happens when there is a little bit of degradation and or inhibition. Here we see that very same sample, the same DNA profile that was present in the previous electropherogram, but now before the DNA got amplified, it was degraded and inhibited a little bit. And what happens to the heights of the peaks? Notice the heights on the left-hand side of the electropherogram all the way across for all the different colors are still pretty tall. But now the peaks on the right-hand side of the electropharogram are getting shorter, and that decrease in height is progressive. As we move from left to right, the peaks seem to get smaller and smaller as we go. Instead of drawing a line that's a straight line, a flat straight line, to show the heights of the peaks on these electropharograms, now when we draw that line, you get this slant. You get what's often referred to by DNA analysts as a ski slope, where the peaks on the left side of the electropharogram are taller as a rule than the peaks on the right-hand side of the electropharogram. This has all the hallmarks. It looks to me, and I hope it looks to you, as a sample that has experienced at the very least degradation, at the very least maybe inhibition, maybe both. Can't necessarily say which has predominated, but this is a sample that looks as if it's been degraded or inhibited. Why might you care if a sample has been degraded or inhibited? Well, there's a good reason that you might care about this particular problem associated with DNA profiling results, because degradation and inhibition taken to their extreme can alter what information we get from electropharograms. Let me show you this next slide, which takes degradation and inhibition just one step further. The slide that we've been looking at is one that has slight degradation and inhibition. Now let's take a look at one that is more degraded and inhibited. We still see the hallmarks of degradation or inhibition, right? The peaks on the left side of the electropharogram are taller than the peaks on the right side of these graphs. But the ski slope is steeper here than it was on the previous slide, and I want to draw your particular attention to things that are happening way at the right-hand side of the electropharogram. Remember, on the right-hand side, that's where the DNA fragments that were being amplified, the pieces of DNA are the biggest when we get to the right-hand side. That's where degradation, that's where inhibition are going to manifest themselves the most. And look what can happen when degradation and inhibition play out. In a word, we can have this phenomenon known as allelic dropout take place. No DNA analyst wants to see indications of allelic dropout. Allelic dropout quite simply means that the test has failed. It hasn't given us the information that it should have given us. It hasn't given us the information that we had hoped it would give us for at least some parts of the DNA, the loci that are being tested by the kit that's being used. We're getting an incomplete picture of the actual DNA profile when dropout has occurred. And with degradation and inhibition, dropout can easily occur, particularly for the loci that give rise to peaks on the right-hand side of these electropharograms. If you don't recall from the previous two slides, there are alleles that were present in the less degraded sample that simply are not showing up now in this more degraded sample. These arrows will help you see, or perhaps refresh your memory as to where those peaks were. But we've lost here 6 different alleles that we know are actually present with the sample, right? The sample hasn't really changed that much. The source of the sample is the same. What's happened is that this sample now has become more degraded, more inhibited than what we had seen before. We're getting a less complete look, and that less complete look is manifesting itself here by having us not get some alleles showing up, not being labeled, even though they had been in that underlying sample. I often have attorneys, when I'm talking with them about DNA profiling test results, I'll often have attorneys ask me, does degradation, does inhibition, is it possible to change an individual's DNA profile? And I think the short answer to their question, if I understand what it is they're asking, is no. Breaking down DNA molecules does not change a DNA profile. But breaking down DNA molecules can change what we think a genotype for a sample is. So this is it's a subtly different question. The DNA isn't changing. We aren't going to see instances where a chemical will convert a 12 allele and a 15 allele to a 9 and a 13 allele. That sort of change doesn't happen. But what can happen is this, and it could be every bit as concerning as that other kind of change. You might change a 12 and a 15 to a 12 and nothing else. That's different. That's the DNA profile of a different person, and we may end up thinking that somebody is excluded as a possible contributor because they have a 15, and we don't see the 15 in the evidence sample, but the reason we didn't see the 15 in the evidence sample isn't because it's not there, it's because it's dropped out. Dropout is a problem, and it's something that is very difficult to quantitate. We can often suspect that dropout is occurring. Sometimes our suspicions are more than others, but the most likely loci to have dropout occur are the ones that you see on the right-hand side of an electropherogram, and you're most likely to expect dropout is taking place when you see this ski slope effect, and sometimes loci with absolutely no information at them whatsoever. If you look at this electropherogram at the D18 locus, there are no alleles labeled at all. We know that dropout has happened there. That's not just allelic dropout. We can say with confidence that that locus has dropped out. That's locus dropout. Here's another instance of locus dropout, but here we can tell because we know what the underlying DNA contained, but these are instances of allelic dropout. One allele remains. If we didn't have a reference sample to compare to, we might mistakenly come away saying that the contributor to this sample at the D7 locus was an 8-8, whereas we know from our other tests that because of the degradation that there was another allele that simply failed to be detected after degradation or inhibition had taken place. So these are technical artifacts. These are commonly encountered technical artifacts that show up quite frequently when we're looking at DNA tests that originate from evidence samples. Many of these artifacts, stutter, spikes, and blobs, those are things that often show up in reference sample. Peak height imbalance and degradation and inhibition, that's more of a type of problem that manifests itself with evidence samples, but they can occur in reference samples as well. Often they can be recognized. When they are recognized, at the very least, they raise some questions about how certain we can be about the reliability of the test and the conclusions that can be drawn from it. Sometimes serious concerns, sometimes not as serious. All right, so those are technical artifacts that can complicate the interpretation of DNA testing results. Let's move to the last bullet here, the last topic for these factors that can be a problem with interpreting test results, and that is this business of background noise. Just as with peak height balance, I think perhaps the best way to start talking about background noise is by showing you an electropherogram where we're not concerned about background noise. The issue here with noise is very simple. We need to be able, when we're doing interpretations of electropherograms, to distinguish reliably between what is signal and what is noise. That's the crux of the problem. And it's not a problem unique to DNA profiling and interpreting of electropherograms. Many people have had to wrestle with this business of distinguishing between signal and noise long before people were concerned about doing it in the context of DNA profiling. The signal in an electropherogram is pretty straightforward. It's the peaks. It's the peaks that arise from the amplified DNA that were amplified during the PCR amplification process. And again, this is an electropherogram where there is no question as to where's a peak and where's not a peak, right? If you look at the D8 locus up here, there's a 12 and there's a 15. I don't have a lot of concern about there being a 16 or a 17. That's signal. There's nothing going on signal-wise there. There might be a little bit of noise, right? But I'm not worried about confusing signal and noise because the signal here is so easy to distinguish from the noise. So, not a problem, right? But again, where I'm going is we'll start with a sample that doesn't have a problem with a signal-to-noise ratio and move now to one where that may be more of an issue. Consider this electropherogram. Here, there are some instances where we can look at a peak and say, yep, that's a peak, that's signal. It's not too hard to pick some of those out, right? At the D3 locus, there is a 15. Yeah, that's signal. There's also a 16. Yeah, that's signal. It's hard to be worried that that might be just a random perturbation associated with the baseline. Those are big, strong peaks. They're very tall. That's signal. Next to the 15 and the 16 is a smaller peak, a 17. Again, just to be consistent with things that we've been talking about in other videos here, this is a clear indication that we're talking about a mixed sample. If that 17 is real, and we could probably say that it is signal rather than noise, then we're talking here about a sample that's a mixture of at least two people, just based on what we're seeing at this one locus, because one person shouldn't be contributing more than two alleles to any given locus. So we see a third peak. We might wonder, could that be baseline noise? I think that would probably be something that we could resolve pretty quickly and easily. A survey, a poll of individuals would probably be pretty comfortable in saying that's signal. I'm not too worried about it being some sort of baseline fluctuation. It's easier at this locus, but at some loci we might start to worry. Let's look at this locus, the D16 locus. Here, there are two peaks that are pretty tall, 278 for the 10 and 492 for the 12. Those are relatively tall peaks. I'm not too worried about them being noise. But the computer software has also labeled two additional peaks, this 9 and this 11. The 9 is only 85 tall. I see some little blips over here just to the right of the 12 that aren't quite so tall as that, but nonetheless, that's making me wonder, maybe there's more stuff going on here. Maybe there is some sort of noise happening, right? Sometimes it's a little harder than others to distinguish between signal and noise. I'll tell you what laboratories have done to help make it easier for them to deal with this question. What they've done is this, is they've settled upon something known as a minimum peak height threshold. If a peak doesn't rise above a certain level, they're prepared to just write it off. Walk away, don't say anything about it. We're not sure that it's signal as opposed to noise. We're not going to take a chance and draw any conclusions from it. We're going to walk away. It falls beneath a minimum peak height threshold. For most laboratories that settle upon a minimum peak height threshold, they've chosen a value of 150 RFUs. Now, there are some laboratories that draw their line in the sand at about 200 RFUs. There are others that go down as low as 100, and some go to 50. There's one laboratory I know of that goes as low as 40 RFUs. That's the line that they draw. Any peak below that threshold, they say they can't reliably distinguish between signal and noise. They have concerns about how reliable the information is there, and so they're simply not going to draw conclusions from it. Where did that, well, what are the implications of that? For this particular electropherogram, if we draw the line at 150 RFUs, that's going to have implications for how we interpret some of the peaks that are labeled by the computer here. Specifically, the ones that are circled in red fall beneath that 150 RFU threshold, and the computer then, if it's operating with a minimum peak height threshold of 150, would not put a label on those peaks. There would be nothing on the printout of the electropherogram that would tell us those peaks are actually there. Okay? You'd still be able to see the peaks as bumps on the graph, but the labels would be gone, and you would be getting a message that the computer had been told that those peaks may not be reliable. We're not going to include them in our analyses. For this particular electropherogram, you can see that's going to have implications for what? 5 different red circled peaks. And there's potential here for alternative interpretations of what's going on there. Somebody might want to look at those peaks and say, well, you know, I do think that 11, for instance, at the D13 locus really is there. It's pretty close to the minimum peak height threshold. It looks different than random noise. If it's really there, that could easily have some implications for the interpretation of this sample. You may be able to include somebody as a possible contributor if the 11 is really there, as opposed to if it's not. By the same token, you might be able to eliminate somebody as a possible contributor on the basis of the presence or absence of some alleles. I think it's easy to imagine how where you draw that line and what you do with the peaks beneath the line could be a matter of some contention. It wouldn't be hard for one side of a criminal prosecution to say that peak is important and it really is there, and for another to find the other side to find a good reason to argue that it's not really there. Where there's room for controversy, it makes interpreting DNA profiling complicated. So it's worthwhile to ask, where did those minimum peak height thresholds come from? What's the genesis of this idea of drawing a line across an electropherogram? Because I can tell you this, I've asked many DNA profiling analysts over the years, do you know of any other discipline? And I don't limit it to just DNA profiling experts. I've asked scientists, physicists, you name it, who else draws a line in the sand like that, a minimum peak height or a threshold above which you say you have noise, below which you don't? This is a phenomenon that is unique to forensic DNA profiling. No other discipline that I know of draws a line like that to distinguish between signal and noise, between signal that can be relied upon and signal that's less reliable. This is a fairly unique phenomenon. Its genesis in the field of DNA profiling goes back pretty much to the origin of the test kits that are used today by most of the laboratories around the world. That manufacturer of those test kits is Applied Biosystems. They did a validation study in 1988 that was published in the Journal of Forensic Sciences. You can read that validation study in all its glory by following this particular reference. But let me draw your attention to one particular paragraph that is, more than anything else, where it is that the idea of a minimum peak height threshold comes from. In fact, to my knowledge, this is the first time that those words were strung together in a sentence in any sort of document associated with DNA profiling. This paragraph, if you take the time to read it, tells you that the minimum peak height threshold as it was originally conceived was actually intended to do something different than what it's actually been used for over the past 15 or so years that people have been relying upon minimum peak height thresholds. The essence of what this paragraph is saying is this, and I'll leave it to you to read it and get your own interpretation if you like, but the essence is, when small amounts of starting material are used to generate DNA profiles, there can be problems with allelic dropout, which we've already talked about, and peak height imbalance and exaggerated stutter, all things that we've talked about earlier in this video, that you don't see happening when you're talking about starting with larger amounts of starting material. And how did they know if they had small amounts of starting material as opposed to large amounts of starting material? Again, it's based on the heights of the peaks. High peaks come from large amounts of starting material, small peaks come from small amounts of starting material. And the minimum peak height threshold was essentially a safeguard against trying to draw conclusions when you've got too little material to get a reliable result. It didn't have anything at all to do with distinguishing between signal and noise, and yet, to a large extent, crime laboratories that do DNA profiling have been using it for that other purpose, as a quick way of eliminating from consideration the possibility they're confusing signal with noise. In such circumstances, laboratories have argued that what they're doing is conservative, right? They're disregarding things that may not be reliable. We all would support their using their most reliable information, right? And so by setting aside unreliable information, they say that they're being conservative. But at the same time, we have to bear in mind that while they're eliminating noise from the mix, and we don't have to be concerned about noise, it might also be that some signal is being lost in the process. There's truly an element here of throwing out the baby with the bathwater, or at least a potential to throw out the baby with the bathwater. And quite simply, it's possible we're removing signal that's really there. And it also fails to take into account that when a laboratory draws that line, let's say at 150 RFUs, that they've established where they think they can distinguish between signal and noise at a particular point in time, and that reliability, that ability to distinguish between signal and noise, may well change over time. The instruments may get older and more prone to noise. The instruments may get older and less prone to noise. The reagents that are being used might be more or less prone to noise over time. The analysts using the instruments may cause them to be more noisy as they get lackadaisical with time, or less noisy as they become more proficient in the use of the equipment and the instruments. Those things can change. Here's the thing. Any other discipline that needs to distinguish between signal and noise doesn't draw just a line in the sand. They're sensitive to the fact that signal and noise ratios can change over time. What chemists do is something that I think DNA analysts can take a lesson from. They rely upon something known as a limit of detection and a limit of quantitation. This next slide gives you a sort of a graphical impression of what it is that we're talking about with the limit of detection. For any kind of instrument that's recording voltages or light impulses, there's going to be a fluctuation of the baseline, just a random noise, a static sort of effect. Sometimes the static will be for an instant louder than at another time, right? We can measure the heights of those random bits of noise and get an average value and a standard deviation associated with that average value for the background noise, the stuff that's just going on along at the baseline. And a limit of detection then is simply this. It's the average level of noise plus 3 standard deviations. From a statistical perspective, we can say this. If you find something that rises above that level, the average level of noise plus 3 standard deviations, it's very unusual noise, or it's something else, right? 99.7% of noise, on average, a typical bit of noise would fall beneath that line, okay? By the time you're up to 10 standard deviations above the mean, now we can be so sure that what you're looking at is signal as opposed to noise. That's extremely unusual noise to get that loud. We can be so sure that it's that far above the noise levels that we don't even have to worry about the peak's height, in a DNA profiling sense, being compromised or influenced significantly by a contribution from noise. Okay? So we can quantitatively quantify how much signal is there without worrying about it being polluted or not polluted by a contribution from noise. When it gets above 3 standard deviations above the mean, we can be sure that we've detected something that's very unlikely to be very unlikely to be noise, and that in turn probably leaves us with the only other alternative, that it's signal. With an electropharogram, there are lots of opportunities to get a feel for how much noise is going on at the background level. This is an electropharogram that shows you a positive control. We know where the peaks should be for a positive control. Pretty much anywhere else on this electropharogram, aside, say, from the 16 and the 17, that is background noise. And we can assess the average value and the standard deviation and use that to determine a limit of detection and a limit of quantitation. And if you're wondering, is it worth the trouble? I mean, does it have a practical application to dealing with DNA testing results? Well, let me suggest this. Let's consider this slide. We have here a sample that we know is a mixture. It comes from a testing laboratory's validation studies. It's a 10-to-1 mixture of a female's DNA to a male's DNA. We know it's a mixture. This testing laboratory had in place in its protocols a minimum peak height threshold. They drew the line in the sand at 150 RFUs, and they said any peak that fell below that line in the sand, any peak that fell below that could be noise, weren't sure it was signal, they aren't going to talk about it. If you draw that line in the sand at 150 RFUs on this electropharogram, I'll tell you what you see. You only see peaks that correspond to the major contributor to this mixture. Only the female's DNA rise above that minimum peak height threshold. But I'll tell you what else. If you are willing to drop the line to a limit of quantitation, this dashed bluish line, or to the limit of detection, you know what happens? Is suddenly this moves from being a sample that is a single source sample with peaks that could only have come from one individual, the female, to now being a mixture, an obvious mixture, a mixture with a major contributor and a minor contributor. And I tell you what, there's not a single peak from the minor contributor, the male in this case, that wouldn't be detected if you went down to the limit of quantitation. And there's not a single peak that you pick up that you would later on say is noise, because it didn't come from these two known contributors. The bottom line, by using this more statistically based approach to distinguish between signal and noise as opposed to a minimum peak height threshold, we've been able to convert this sample from one that looks like a single source sample to a mixture of a major and a minor contributor. And I'd like the attorneys who might be watching this video to stop and think what the implications of that might be. Consider that this might have come from a rape investigation. We may have just made this sample probative, useful evidence that would help incriminate or link a male to this particular sample that we wouldn't have bothered to talk about if we had just been talking about the minimum peak height threshold results. All right? This could have some important implications. A prosecutor could look at this and say, wow, I need to have that level of understanding of the signal versus noise because that's going to allow me to help identify a suspect. A defense attorney could look at that and say, I need to look at that level so that I can see if it's my client's DNA that's there or not, because if it's not my client's DNA that's the minor contributor, I've got an alternative theory that I want the jury to hear about for this particular case. Bottom line, I think a very good argument can be made for using limits of detection and quantitation in lieu of minimum peak height thresholds to distinguish between signal and noise. And I'm not alone in thinking that. A number of laboratories have made that switch over the past few years. Hopefully more will soon as well. So where have we been during the course of this video? Well, again, this video was all about talking about factors that can make interpreting DNA profile evidence, electropherograms, a little bit more complicated than you might have thought if you had only cut your teeth looking at reference samples. These are the sorts of things that come up time and again when we're talking about issues that make interpreting evidence samples a little bit more complicated. It's not always black and white. There can be shades of gray in terms of interpreting. Is this an artifact? Is this noise? Or is it signal? Is it something that tells us there's an important DNA contribution to a sample? Where there's room for debate, there's room for argument in court about what weight should be attached to these samples. And that is probably the crux of the issue here. But for now, I think we can wrap up this particular talk. This has been my effort to have a video that gets you up to speed about complicating factors associated with the interpretation of DNA testing evidence.